Hi everyone. In this video, I'll be discussing about the transformer architecture. So I think you know that transformer is the core architecture behind all the large language model. So if you want to understand the large language model, how it works actually, how it takes the entire input from the user, how it let's say remember the previous context. So first of all, you have to understand this particular architecture because in this architecture there are some very amazing concept actually has been used. So with respect to that particular concept, this architecture can work with actually very complex kinds of data. Okay, and it will give you like good performance. So if you search over Google the transformer architecture, so you'll get this particular paper link called attention is all you need. So this is the official paper from the Google site. So Google has published this particular architecture. So Google has published this particular paper and you can see the author name. Okay, so these are the author, actually they're from Google brain team. Actually they developed this particular architecture. So if you have time, you can go through the entire paper, guys. You can see this is the paper introduction, background. Okay, and this is the architecture of the transformer. Now at the very first time, if you're seeing this particular architecture, I know that it would be a little bit hard to understand. Okay, whatever let's say things they have mentioned here. So I'll try to break down the architecture, then I'll try to discuss. I think then after that this part would be more clear. Okay, so guys, what I'm going to do, I'm going to break this architecture. Okay, and I will try to discuss each and everything. For this I'm going to refer one amazing blog from LLMR. So if you search like LLMR actually transformer architecture, so you'll get this particular blog. Okay, the first website, this is the blog. So he has actually created this particular blog in an amazing way. He has used actually lots of visualization to explain the transformer architecture. So the entire video I want to dedicate to JLMR because of him actually I was also able to understand this particular transformer mechanism. Got it? So guys, you can see this is the blog. So first of all, he has shown like the high level overlook of the transformer. Let's say initially you can consider transformer is the black box. Okay, this is the transformer. So here let's say you are giving one input and you are getting an output. So the example he has shown with respect to the language translation. So he is passing actually French language and he is getting a English output. Okay, as in so here he is passing actually French input and he is getting English output. Got it? So initially let's say this is the transformer. So if you give any input, so it will return you some kinds of output. Now if I show you inside the transformer what we have. Okay, inside the transformer what we have, you can see inside the transformer we have two kinds of layer. One is the encoder layer, another is the decoder layer. So those who have already studied about basics of NLP, I think you know that inside NLP, inside RNN actually we have some networks like LSTM, GRU, okay, encoder, decoder. So these are the architecture were available. So this is the same encoder and decoder architecture. Now what we'll do, we'll just try to see what we have inside encoder and what we have inside decoder. So guys, you can see we usually pass the input to the encoder layer and decoder layer gives us the output. So here we are passing the French input to the encoder layer and it is going to the decoder layer. Okay, after doing some pre-processing, and decoder layer is translating this particular French to English and it is giving you the output. Okay, that means inside encoder and decoder some mechanisms are happening. We'll try to see what are the mechanisms are happening. Okay, everything we'll try to discuss. Now see guys, I will suggest you after this particular video, just go through this particular blog and just try to read these are the, let's say, text. Okay, whatever he has written, see whatever things I'm going to explain through the entire video. So the same thing you will be getting, okay, with respect to the text. Got it? So first of all, try to watch this particular video, then go through this particular blog and try to read everything whatever he has written, then your understanding would be more clear. Got it? Now you can see guys, in the encoder layer, okay, in the encoder layer we have, okay, we have 8 encoder layer. We have 8 encoder layer. It's not like that they're only using one encoder layer. No, they are using, okay, 8 encoder layer. You can see 1 2 3 4 5 6, 1 2 3 4 5 6, sorry, 6 encoder layer. Okay, not 8, this was my mistake. 6 encoder layer actually they're using in one encoder, okay, layer. Now inside decoder again you have 1 2 3 4 5 6 decoder layer. Got it? That means whatever input you are passing, it will go through 6 encoder layer. then some pre-processing would be happening, some processing would be happening, then it will return the output to the decoder. Then again the output will go through the 6 decoder layer and you will be getting the output. Okay, I hope it is clear. Now you can see guys, in the encoder layer we have two kinds of layer. One is the self attention and the feed forward network. Okay, I'll be talking about the self attention. What is self attention exactly? And I think you already know what is feed forward, forward neural network. Okay, feed forward neural network is nothing but it's a artificial neural network, dense layer. Okay, I think you know that all the architecture has this particular feed forward neural network. Okay, at the last layer, so that's why they're also using that particular network here. Now you can see this is the overview. So in the encoder layer we have self attention and feed forward, and in the decoder we have self attention, encoded decoder attention and feed forward. Okay, now what is encoder and decoder attentions? That means after explaining this particular self attention, okay, I'll talk about this part, but you can consider they're combining encoder and decoder attention layer together and they're using inside the decoder. Okay, this is another layer actually they're using inside decoder. That's it. Now let's try to see one example. So let's say this is our input x1, x2 and x3. So here we are passing a French sentence, you can see. So this is the French sentence, and here is my architecture. So this is the French sentence actually I'm passing. First of all, it will go through the encoder layer, and encoder layer has how many encoder layer? I think you know that 8 encoder layer. 6 encoder layer. And in one encoder layer, what we have? Okay, we have two kinds of layers, self attention and feed forward. So first of all, it will go to the self attention, and self attention will return some output like z1, z2 and z3. Okay, then it will go to the feed forward, and feed forward will give you some output. Now how this z1 and z2, z3 we are getting, we'll try to understand. Now you can see guys, here is the let's say demo. So LLMR, what he did actually, instead of taking 3 let's say word, he has taken 2 words just to explain the things easily. So now let's say this is our words, thinking and machines. We are passing to the self attention, and self attention is returning one output z1 and z2, and we are passing it to the feed forward. Feed forward is giving me one output, let's say r1 and r2, and this particular output we are passing to the another encoder layer. That means we have 6 encoder layer, right? So it will go through the 6 encoder layer like that. Okay, dot 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 like that. So now you can see self attention at a high level, how it works. So let's say this is one sentence I have. The animal didn't cross the street because it was too tired. Okay, it was too tired. Now here you can see it was too tired. Now what this it represents? So as a human, I think you understand it represents the animal, yes or no. But what about machine? How machine will identify this it is the same thing as the animal? Okay, for this we have to apply the self attention. Okay, now you can see this is the like your entire sentence. The animal didn't cross the street, it was too tired. Now to represent it, actually it is giving the attention to this particular word. You can see the animal didn't. Okay, so these are the word actually it is getting attention. Okay, to represent the it. Now how it is getting the attention? Okay, we'll try to understand how it is giving this particular word as an attention. Okay, so we'll try to understand this particular thing. Now you can see some of the word is getting very less attention. You can see because of this line is like very what I can say, it's not visible properly. Okay, now you can see self attention is detail. So how this self attention happens, we have actually so many words, but how it will give the more attention to the specific word, we'll try to understand from this particular example. So let's say this is our word thinking and machine. So first of all, what we have to do guys, I think remember, first of all we usually generate the embeddings, like we convert this text to the embedding model. Okay, sorry, embedding representation. Okay, embedding numbers, that means the vector numbers. Then what we do guys, we initialize some weights. I think you know that in neural network we initialize the weights, right? So in this case actually we initialize 3 kinds of weights: w, wq, wk and wv. Let's say this is our weights. Okay, now to represent this queries, keys and values, what needs to be done? So you will be multiplying this x1 with w1. Okay, x1 with x1 with wq. Okay, x1 with wq, then you will be getting q1. Okay, then if you multiply x2 with wq, you will be getting q2. So similar wise, if you multiply x1 with wk, you will be getting k1, x2. So here see the calculation is happening like that. So let me take the pen. So x1 is getting multiplied with wq and you are getting q1. Okay, then x2 is getting multiplied with wq and you are getting q2. Then again x1 is getting multiplied with wk, so you are getting k1, and x2 is getting multiplied with wk, you are getting k2. Then x1 will multiply with wv, you will be getting v1, and x2 will multiply with wv, you will be getting v2. Okay, so that's how you are getting query, keys, and value. Okay, these three particular vector you will be getting and will be naming as query, keys, and values. Okay, I hope you got it. Now let me just clear everything. Now we can see, guys, we are the query, keys, and values. Okay, vector. Now here you can see this is the another example. So let's say this is our word. We did the embedding generation, then we got q1, k1 and v1, that means query, keys, and values. Okay, and how, I think I already showed you. Now you have to like get this code. Okay, how to get this code? You have to multiply this q1 with k1. Okay, q1 with k1. So if you multiply, you will be getting this particular number. Then again, for the machines, what you have to do, you have to multiply q1 with k2, and you will be getting the number. Now you can see, I mean, which word is having more number? So definitely thinking is having more number here. Okay, 112. So thinking is having more number than the machines. Machine is having 96 and thinking is having 112. Okay, now here will be like generating some, let's say, I mean, percentage number. For this, some more calculation needs to be done. You can see again the same thing is happening. We are getting the score. Now we have to divide this particular score by 8. Okay, then after that you will be getting the number. Then you have to apply the softmax activation function. I think you know what is softmax activation function. It will give you the probability number. Okay, so in this case we are getting 88% probability of the thinking, and machines we are getting only 12% probability. Now that means your model is giving more attention to the thinking words. Okay, your model is giving more attention to the thinking words. That means thinking words is important. Okay, in this particular sentence. Okay, so that's how actually this particular self attention works. It will give you the attention like that. So these are the calculations you will be doing, and it will give the calculation like that. Okay, now I think you are getting. Now one thing, so after doing the softmax, you have to multiply with the value. So this particular value you have to multiply, then we'll be getting the z1 and z2. Now I think you understood so why we are getting the z1, z2 here. Okay, so after going through the self attention, z1, z2, and so on. Okay, so now I think this particular I think part is clear. Okay, what is z1, z2, and so on. So yes, so the same calculation I showed you, so he has also shown with respect to the graph, with respect to the matrix. So first of all, you have the input, then you are generating the keys and queries and these particular values. Okay, by multiplying with wq, wk, and wv. Then after that you are applying the softmax activation function. Okay, then you are getting the z1, z number. Then see, this is for the single head attention. Okay, only single head attention. And what is the problem with single head attention? See, some of the word is getting ignored here. Okay, you can see this line is not visible. To represent it, actually these are the word is also required. Now to prevent this particular issue, they have introduced something called multi-head attention. Okay, multi-head attention. So instead of using single head attention, see the calculation we have done, it is only happening with a single head attention. Now what is the main benefit in the multi-head attention? They are using more attention layer. Okay, they're using more attention layer. How many attention layer? They're using 8 attention layer. Okay, you can see calculating attention separately in 8 different attention heads. That means the same attention, whatever calculation I showed you so far, they're using the same attention mechanism, but they're doing in 8 attention layer. Okay, 8 multi-head attention layer. Okay, that's why they're calling as a multi-heads. Okay, multi-head attention. The same calculation, you can see the same calculation, and after that we are getting z1, z2, z3, and so on. Then we are doing the summation operation. Okay, then we are only getting 1z. So see, this is the entire calculation. Okay, with the multi-head attention. Now after doing the multi-head attention, this is the results, guys. Okay, you can see now those word actually was getting ignored, now it is also trying to capture. Okay, now you can see amazingly it is trying to capture. So this is the main benefit to use the multi-head attention. Okay, now transformer, whatever let's say large language model will be using, all the large language model use the multi-head attention mechanism in the backend. So these are some more visualization you can see. So this is the visualization. Now now we'll try to understand the positional encoding concept, like how this positional encoding works. So what is positional encoding exactly? So see, here you initialize one vector. Okay, this particular vector you initialize like t1, t2, and t3. So what happens actually, this positional encoding, see, it will try to capture the semantic meaning, okay, of your sentence. Let's say you have passed one sentence, they switch, okay, edutient. So after the switch is coming, okay, after switch edutient is coming, how your model is trying to understand this thing because of the positional encoding, because this is the vector, this is another vector, this is another vector. Now what you have to do, let's say if you subtract this vector with respect to this particular vector and this vector with respect to this particular vector, which will have very less, let's say, distance, definitely this will have the less distance. Okay, that time I can consider this switch is nearest to the JE. Okay, then this edudent. Okay, so that's how actually they are getting the semantic information, semantic meaning. Okay, after this JE, switch is coming, after switch this particular edudent is coming. Okay, that's why they're trying to capture the semantic information with respect to the positional encoding. So that's why it is also super important, because you will be passing actually very big prompt here, big, let's say, input, and to capture the semantic information, this is the way actually they're using. Got it. Now let's try to see the next thing. So see guys, this is the positional encoding concept. It's a vector only at the end, and if you just do the distance calculation with respect to all the vector, you'll see that this particular word will come nearest to this particular vector. Now these are some actually visualization graph he has shown. Now there is another concept inside this transformer architecture called residual block. Okay, so those who have started computer vision like CNN architecture, I think you know that there is an architecture called ResNet 50. Okay, so ResNet 50 has also this residual networks. What is residual networks actually? So it has actually one skip layer. So why we use the skip layer? Because sometimes, let's see, if you have very less complex data, so by going through some actually layer, you will be able to get the higher accuracy. That time you don't need to go through all the layer. That time actually what it will do, it will skip the, let's say, layer. Let's say this self attention is not required. Directly it will pass to the normalization. I think you know what is normalization. It will normalize the data. Okay, then after normalization, let's say it will again jump to the another normalization instead of feed forward neural network. Okay, so that's how it will skip automatically based on the performance of the, let's say, loss function or whatever actually you are using internally. So the same thing, whatever you have learned in the ResNet architecture, the same concept also using here. Okay, if you are not understanding, if you're not sure about the let's say ResNet architecture, you can go through and you can see that, okay, how ResNet architecture works. Now here you can see guys, this is the entire architecture overview. Now this is the final one. So we are passing the words and it is going to the encoder. Inside encoder we have self attention, some normalization layer they have also added, and feed forward again some normalization they have added. Okay, then again it will go to the next one. Okay, next one will pass to the decoder. Okay, that means 6 encoder it will be passing, then it will go to the decoder layer. And so decoder actually, again you can see I have self attention, normalization, and encoder and decoder attention. That means encoder and decoder they have combined and they have created one architecture and they are using inside this particular decoder. Okay, and this particular output will go to the decoder. Okay, decoder second layer of decoder. Then after that they are applying the linear. Okay, then they are applying the softmax and we are getting the output. Okay, now you can see guys, these are some visualization. You are passing the input, it will go to the decoder. Okay, and some processing is happening. Okay, and you are getting the output. Hi, got it. Now let me show you the entire visualization, how these things working. You can see. So if you have time, just try to open the this blog and you will be able to understand, okay, how things are working. See, it will coming here, and again the output we are getting here, it is going as an input to the decoder. Okay, and it is predicting this one. See, so this is the French and this is the English translation of that. And whenever you are getting end of the sentence, that means your sentence is done. Okay, your execution would be terminated that time. Okay, that's how the entire architecture works. Okay, now guys, see, these are the things are not required. Yeah, so this is the actually mechanism of our transformer architecture. That's how actually self attention works. Now going forward, whatever LLM you will be learning, okay, all the LLM are using this particular transformer architecture in the backend. Now if I open this particular architecture, now if I show you, you will see here, and now I think you will be able to understand what is input embeddings, what is positional encoding, okay, what is multi-head attention, what is normalization, what is feed forward, again what is normalization, and this is called actually our encoder layer. Okay, then we are passing the output to the decoder layer. Okay, that means in the decoder we have mask multi-head attention. That means encoder and decoder, okay, both I mean combined architecture. Then normalization, then again a multi-head attention, then normalization, feed forward, normalization, linear, and softmax, and we're getting the output. That means this is the entire decoder layer. And again we're using positional encoding, okay, just to get the semantic information. Okay, now this particular architecture, this JLMR actually break down, okay, in this particular block, and he has explained each and everything with respect to the visualization. Okay, so this is one of the amazing blog, guys. Again, I'll try to suggest you just go through this blog and try to read everything, whatever things I have explained so far, everything he has written, okay, with respect to the text. Now you can also go through the paper. Also in the paper they have also, let's say, mentioned the mathematical equation and all. If you're interested, you can also go through this particular paper. So yes guys, this is all from this particular video. So here we have explained about the transformer intuition. I hope you have liked it. Thank you so much.